Hello, today we're going to talk about our final project for EE504. My name is Jules,
My name is Micah.
and we're going to talk about TPMS sensors. So what are TPMS sensors? First of all, TPMS stands for Tire Pressure Monitoring System, and it allows vehicles to know what the tire pressure of each tire is by reporting the value to the ECU and then displaying it to the driver, either on the dashboard or on the infotainment system. And it's crucial for safety because it's good to know your tire pressure. It's been enforced to be in each of any car since September 2007, but they've been around since the 1980s, mostly in luxury vehicles. And as you can see on the picture, they are on the valve on the stem in which you put air to inflate your tires, and they're encased in some kind of plastic to make them weatherproof. And there are different brands of TPMS sensors depending on the manufacturer of the car. And each of the sensor is going to use a slightly different protocol and packet structure, which is something that we figured out. And in those packets, there's different bits of information, like the tire pressure, of course, but also an ID so that the car knows what wheel is talking, as well as temperature and sometimes a battery status indicator. And that data is transmitted over one of two carriers, either 315 megahertz or 433 megahertz, depending on the region. Usually in Europe, it's 433 megahertz, and the rest of the world uses 315 megahertz. So the first thing we had to do is figure out how to receive the packets and how they were transmitted. So what we did is we used a spectrum analyzer to look at some data, and we figured out, as you can see in the picture, that the packet is sent over a short period of time in a burst sequence. And looking at the output of the spectrum analyzer, it looked like it was FSK. And that was confirmed by some searches on the web, where we found that the signals were most likely FSK and that they would be Manchester encoded. And it's also good to know that that data is only transmitted when the vehicle is moving. The TPMS sensors know that through the use of an accelerometer. And since we also figured out that all the brands would have different kinds of packet structures, we decided to focus on one of the most common types of sensors, which was the Toyota TPMS sensors. And we were able to gather signals throughout the project from up to about 100 feet away, which is pretty good. And so we took different steps for analyzing and decoding the packets. We acquired a secondary SDR, the NESDR Smart by Newelec, and we used some open source software called RTL433 to look at the packets and have a reference point to compare our results to make sure we decoded them properly. As you can see in the bottom left, that's the output of the RTL433 software. And to the right are files that we found in the open source repository of that software that informed us on the packet structure and what the preamble would be, which is important if we want to reverse engineer it ourselves using the Pluto SDR in MATLAB.
Okay, so now that we know the modulation scheme is FSK, we could then use the signals that we received and demodulate those with the SDR that we explained on the previous slide. So the binary code shown here on this current slide, this is the demodulated form of the signal that was shown in slide number 3, where we had that frequency spectrum shown. As far as this specific packet goes, we confirmed this was a Toyota TPMS packet, and we know this because of the 14-bit preamble that precedes the 9-bit encoded data. So the 9-byte, or sorry, not bits, but bytes, these 9 bytes are differential Manchester encoded. So now we have to come up with a scheme where we could decode these bytes. And this is where we get into our MATLAB implementation. Given the demodulated signal on the previous screen, we now want to take this signal, first of all, decode it using differential Manchester decoding. And then once we have those decoded bits, we want to parse through that data packet and extract the information that the TPMS is sending. such as the sensor ID, the temperature of the wheel, and the tire pressure. So now I'm going to exit out of here for a second, and I will show you a live MATLAB demo of this. So first of all, we have to import the signal, the demodulated signal that we shown on the slide. So I will go ahead and plot that and show that here. This is the demodulated signal that we shown earlier. The user is free to go back to the video and confirm that this is indeed the signal that we're trying to decode. So given this demodulated signal, and it's in this variable right here, we're going to input that into our decoding function. And then to decode the signal, we need to know a few pieces of information. First of all, we needed to know that there are 9 bytes in this signal that we need to decode. We needed to know the sampling rate of the SDR, which for the NE SDR, that is 250,000 samples per second. And then this is the bit rate, which describes the amount of time that 1 bit of information is sent. In other words, it takes 96 microseconds for 1 bit of information to. So that describes what this number is. And then in these lines of code, we separate those into bytes, and then we use these lines of code. This comes from the open source software that we described earlier for the specific Toyota TPMS packet, and we extract the information there. And then we display it down here. So we'll go ahead and run this. So according to our function, this is the information that is encoded within that packet. So we encourage the viewer to keep these numbers in mind because we want to verify that these are indeed correct. To verify that these are correct, we also had our SDR output a log of the TPMS packets that it received. And in our case, for the example that we've been using on this slide, it corresponds to the second entry in this log, which indeed comes from a Toyota packet. And according to this Excel spreadsheet, the ID was this number right here. The temperature was 24 degrees Celsius. The status number was 128, and the pressure was 35.75 pounds per square inch. And the user is free to go back in the video and confirm that these numbers are indeed correct and correspond to our MATLAB demo.
So to conclude, what could we have done differently? What could be the remaining steps we could have taken? So first of all, we could have, if we had more time, automated the data collection and decryption in MATLAB, as Micah demonstrated, as well as coding it for the detection of more types of TPMS sensors to cover more vehicles, not only specifically Toyotas. We could also have gotten an amplifier, a bigger antenna to increase the range of detection. And ultimately, we could have coded a TPMS transmitter that could spoof packets and make a car believe, for example, that it's reading a low tire pressure when it is not. We could also have taken the same code we wrote in MATLAB and implemented it in the Pluto itself. Since it's running an embedded version of Linux, we could have had the code on it and have it run in standalone mode using its Wi-Fi hotspot to connect to it and see the data instead of having to use a computer. What lessons did we learn? Well, 10 weeks go by really fast. We had a bit of trouble at the beginning, and then we powered through it, and we wished we had a bit more time to finish the project, but I would say we got to some decent results. We also learned that TPMS sensors are not standardized, and so every manufacturer has a slightly different packet structure, a slightly different transmission speed, and so that's something that we took into account pretty early. And it's also important to know in that case, once we choose one type of sensor, what is the transmission rate, because we need it to decode the Manchester data or the differential Manchester data. And we also learned that reverse engineering is harder than it seems, but while we explored all the paths we could have taken, we learned a lot regarding TPMS sensors. And just a quick note on future applications of what kind of research we did. TPMS sensors could be used in the case of traffic control, and optimization, because you could track where a car is going by just looking at the IDs of each sensors. And if you have receivers at different points in the city or on a road, you could trace what car is going where, and thus improve traffic light timings and GPS ETAs, or just traffic management in general. But no commercial products exist as of today, so that could be a good idea. And this concludes our final project. Thank you for watching.